And now we come to the next section, which is the first use case, which is physics. And we will just start that today. And this slide here is one we've seen before. It describes the physics area. We have at the top right the actual experimental apparatus atlas. At the top left we have the accelerator lying in the tunnel, 27 kilometers in circumference. You can see labeled on that picture the actual experiments: Atlas, Alice, CMS, and LHCb. LHCb is looking for the so-called bottom quark. Alice is looking at proton-ion collisions. Atlas and CMS are doing proton-proton collisions, the sort of workhorse of the Large Hadron Collider. And they have both studied the Higgs particle, which is the particular case we'll do here. This whole field has a raw data to reconstructed data to various fancily named data, AOD and tags, which are basically the raw data information pipeline. Then we have the actual physics step, which is done by taking the raw information, which is the particle position, particle momenta, and types, and converting that into actual physics through histogramming. We already saw an example of that, which we'll repeat. And this is all done on this Large Hadron Collider computing grid, which we noted below has around 200,000 cores, and is arranged across the world with multiple national centers, a giant center at CERN, and each institution has, sorry, not each institution, several institutions have their own component cluster devoted to LHC analysis. The basic information from something like Atlas is a set of events, like is shown in the middle of the slide to the right, which you see these blue and red and yellow lines. These represent the energy and particle vectors produced when two protons collide. This one is an extreme event, namely rather unusual, because typically when protons collide, everything happens in the forward and backward directions. These protons are coming from the bottom left and the top right and colliding in the middle. And the fact that there is a lot of energy and particles going off transverse to that diagonal line is a characteristic of an intense event, which is what the Higgs boson is, because your protons have mass 0.98 of a GeV. The Higgs boson's around 126 GeV, so it's 128 times heavier than a proton. That you will only produce particles of that mass if those protons have huge energy, and when you produce such a particle, it comes from an extreme event which is characterized by these transverse momentas, which are transversely produced particles with transverse energy, which is extreme. So that's actually how they trigger these events, how they identify events of interest. They don't look at all events, they just look at events which could be interesting. This is this picture we saw before. We have the basic analysis in terms of histograms. This is from the Atlas data, looking at the Higgs going to two photons. And we have in the top graph, we have the basic data, which is in terms of number of events, which goes from around 3,600 down to 1,000. The number of events in a bin of size 2 GeV and photon energy. So that's actually got 30 bins, because we're going from 100 to 160 GeV at the 2 photon energy. And then we see a little bump around 126. And that little bump is the Higgs. And at the bottom, and the way we analyze this is we do a model. The model is a smooth curve. That's the so-called background, represented as a polynomial in mass. We add to that a model for how the Higgs should look, which is a spike at a particular energy, smooth, washed out by some smoothing effect, either from data analysis or decay. Uh, and That's the so-called Bright-Wigner form, and that is fitted to the data. And that then we take that graph at the top, and we take the model, and we just plot the result of taking the data and subtracting the background part of the model, and that gives you the signal, which is the Higgs, shown on the bottom graph. As I mentioned before, I was staggered as an undergraduate to learn that bumps were particles, and that's why I studied this field. And the other important observation is errors when you have n events. Remember, n was around 2000 at the where the Higgs is. The error is square root of n. That's the so-called law of large numbers, or the central limit theorem, which we will discuss later on. So here's a little more detail about the Large Hadron Collider. Um, so it's 17 miles in circumference. It's 330 feet below the surface. It has 9,300 magnets, which all use superconductivity. That is a way to get much cheaper high field magnets than you can otherwise. And that allows you to protons run around the ring, getting faster and faster, and eventually they get up to this very high energy, which allows them to collide and produce the Higgs particle. And then here's the amount of energy, 120 megawatts. Remember, that's actually around the size of the very largest cloud center, so it's not a staggering amount, it's just large. As it says here, it's about the same as all the homes in Geneva. And it took a long time to build. There was actually one called the SSC in the USA, which was closed. The one in Europe, fortunately, wasn't closed. It's actually hard to close anything in Europe because you have the European Union, all those countries involved. To close anything, you have to get those countries to agree. So it's hard to get things closed. So if you look at the cost of running CERN, CERN is the laboratory where the LHC is. It's about just computing power costs 286 million and dollars, and electricity for the LHC is 23.5 million per year, and the total operating budget is for the LHC is around $1 billion a year. And if you add up the running costs and the construction costs, they come to some $13 billion, and that's what it took to find the Higgs. That sounds a big number, but it's there are just 50. There are over 50 individuals with net worth of more than that. So it's probably a good investment.